I have the pleasure to introduce Edward Lee. He is extremely, he's very special for various reasons. Of course, he is one of the world-leading experts of cyber-physical systems, has a long history, a long influence on the whole development. And you can see in the chain of universities he passed, this was Yale, MIT, and now he is in Berkeley since '86. But this is not the main reason why it's fun or why he's so special to be here today. Edward thinks very radically in cases. I mean, he likes to go a bit out of the comfort zone also in his talks. And this is always very, very, exciting when he kind of tears on the carpet you are standing on. Okay, we will have a bit of this in this talk. You cannot get all of it because it's a lot. And so I just hand over, Edward. I'm looking for. You need. No, there's also the micro for this for the recording.
Okay. So I need to use this. How's that sound? Good. Okay, so so it's a real pleasure to be here, and thank you, Bernard, for inviting me. It's a particularly suitable crowd because a lot of what I've been doing is kind of at the intersection of formal methods and AI and society, and so here we are, right there. So so let me just dive right in and talk about the dilemma that I am addressing. With apologies to Ina. I fed exactly this text into ChatGPT and asked it to generate an image for me, and this is what it came up with. But the text is, the dilemma is that when we're designing autonomous systems, we want certainty, proofs that only safe behavior is possible. But we also want intelligence, especially the adaptability to circumstances not previously seen. So I'm going to use the word intelligence, for me, does necessarily include this notion of adaptability and an ability to learn, okay? So that, you might not everyone will be using the term that way all the time, but for the purposes of this talk, that's a necessary ingredient in intelligence. So my claim is that these are actually conflicting goals. Now, I want to emphasize this point about learning as being part of intelligence. So in particular, in this group, a lot of the papers have been addressing verification of AI-based systems. But I want to emphasize that using machine learning to design a controller is not the same thing as designing a controller that learns. Okay? These are two different things. Similarly, using machine learning to design a system and then verifying it is not the same thing as verifying a system that learns, okay? And most of the verification that I've seen on AI systems is in this first category, not in the second. I think, in fact, the second may be really, for very fundamental reasons, very much harder. So I want to explain right off the bat that I am a Bayesian. And that means that I have an interpretation of the notion of probability that is intrinsically subjective. Probability is a measure of uncertainty, not a measure of some intrinsic randomness in the world, okay? So when I talk about probabilistic models, that's what I'm talking about, all right? Some people use the terms epistemic versus aleatory probability. Aleatory probability is where you think you're modeling some intrinsic randomness in the world, whereas epistemic is you're modeling what you don't know, okay? So I'm going to start with a really trivial proof of my basic premise that certainty and intelligence are incompatible, all right? It's based on Bayes' law. This image was generated by a natural intelligence, not an AI. And interestingly enough, people pretty much agree that this is not a picture of Reverend Bayes. In fact, there is no rendition that we know of Reverend Bayes, but everybody uses this picture anyway. And if you go to the Wikipedia page on Bayes, this picture will be there, even though that's not him. But okay, so let's do a little math, right? So let S be a statement about which we want to be certain. For example, you're looking at an autonomous vehicle, S is the statement that the car will stay in the lane. And let O be an observation of behavior. So the car followed a certain trajectory, and we've measured that, all right? Then we can relate probabilities about these things, okay? And again, probabilities are uncertainty, using Bayes' law. So let's dive into that a little more deeply, all right? So to use Bayes' law, you need a subjective prior probability, a probability that the car will stay in the lane, okay? That's your prior probability. S is the statement that the car stays in the lane, all right? You need a probability of the observation given that S is true. So if S stays in the lane, what is the probability that the sensors would have told you what they told you? Okay? That's the model there. You need a probability, an unconditional probability of the observation. What is the probability that the sensors told you what they told you, irrespective of whether your prior is true, all right? And from that, you can derive a posterior probability, which is the probability that the car stays in the lane given those observations, all right? Now, the key thing about this posterior probability is that this is a refinement of your prior, an update of your prior, based on the observations, learning, okay? You've refined your uncertainty because of observations that you've made. All right, what about certainty? Well, what do I mean by certainty? Well, certainty is that S is true. You'd like to prove that the car stays in the lane, and once you've got that proof, you know it's true, right? By definition, it's a proof. All right, so what does that mean? Well, that means that your prior is that P of S equals 1. Well, if P of S equals 1, then the conditional probability of O is just equal to the probability of O, and consequently, the numerator and denominator cancel, and your posterior is equal to your prior, and you didn't learn anything. Okay? Observation, no learning. Your posterior is equal to your prior. So we have a second version of certainty. You probably don't want this outcome with the car, okay? The probability that it stayed in the lane was 0. Well, maybe if it's a lane-changing protocol that you're trying to verify, okay? But if S is false, then the probability of S is 0. You're certain about that. The probability of your observation can't be 0 because your sensors just measured it. So it would be sort of silly to say that the probability is 0. And as a consequence, you have 0 divided by non-zero, which will give you 0. And once again, your posterior is equal to your prior, no learning. Okay? So Bayes' law shows us in a rather trivial way that certainty prevents learning, which in some ways seems kind of obvious, right? But is this the real reason for the conflict? So here, I'm going to get less trivial and, as Bernard put it, make an attempt to pull the rug out from under your feet, okay? So I gave a talk on this same subject in Valencia at Date about 6 months ago, and the person who invited me to give the talk told me afterwards that he overheard a table of people talking about my talk at lunch after my talk, and one of them was saying, was he serious or was he just messing with us? And so, to be honest, I don't know the answer to that question. Okay, so let's go into the perhaps more difficult part of the talk, less trivial. All right, so let's look at what is the AI revolution really about? Well, first of all, let me point out that, you know, when I talk about certainty, I'm talking about the kinds of things we can do with algorithms, logic, mathematics, basically rationality, okay? That's the origin of certainty. That's how we build certainty, okay? AIs are realized on computers that use algorithms, right? That's how we're doing them today. So doesn't this put them in the realm of the certain? We should be able to, in fact, be certain about the outcomes because they're algorithmic, right? So Abelson and Sussman expressed very nicely, I think, way back in 1985, what the computer revolution was about. Right? They said the computer revolution is a revolution in the way we think and the way we express what we think. That the essence of this change is the emergence of what might be best called procedural epistemology, the structure of knowledge from an imperative point of view as opposed to the more declarative point of view taken by classical mathematical subjects. So this is a nice picture, I think. It says, okay, this is actually an augmentation of the basic rational principles that we use based on logic and mathematics to add in algorithms, okay? That algorithms can give us foundations that are just as good as logic and mathematics. That's really what they're saying here. So procedural epistemology is about algorithms and proofs. And so the computer revolution is about this realm of the certain, okay? But I think we're in the middle of a second computer revolution. And I don't think that this revolution is usefully described in terms of procedural epistemology. And this is the key point that I want to try to convey here. And I think that it suggests that, you know, we need to sort of, I mean, I think that there may be an identity crisis in computer science that we're facing right now. In fact, there's a very nice workshop being organized in Vienna later this month that is specifically about the identity crisis in computer science. Is this really changing the foundations of our discipline? So my claim, the new machines are not about procedural epistemology. I think it's a complete accident that our brute force implementation of deep neural networks happens to be algorithmic today. And the fact that we use gigawatts to do this is a reflection of this being a brute force simulation of processes that are not at their root fundamentally algorithmic. Okay? That's my essential claim. So how do humans think? All right, well, Daniel Kahneman, who got the Nobel Prize for essentially for this thesis, right, in this book, Thinking Fast and Slow, divides human cognition into two categories. System one is the intuitive, quick, inexplicable decision making. And system two is rational, step-by-step decision making. So when we're in the realm of the certain, when we're doing stuff using logic and mathematics and algorithms, we're using system two really intensively, okay? Those are system two kinds of processes. My claim is that only with system two, in fact, can we achieve certainty. I think deep neural networks are much more like system one than system two. And in fact, they're not all that good at system two kind of reasoning. In fact, one of the reasons that we're looking at all these hybrid AIs where we connect them up with, you know, symbolic algebra tools and things like that is to enhance their system two capabilities, because the intrinsic system two capabilities in the deep neural network aren't that great, just like us. We're not that good at system two either. Human rationality, all right? Well, a rational process is step-by-step reasoning using clearly explicable rules of logic. So another Nobel Prize winner, in fact, until last month, Herb Simon was the only person to have gotten both a Nobel Prize and a Turing Award. Now he's been joined by Hinton in that vaulted scheme. We all know that Tom Hensinger didn't get either one. But he got the Nobel Prize in economics for his thesis of bounded rationality, which essentially says that humans are really not that good at system two, which kind of undermined most of economic theory at the time, which was all about the rational consumer competing in a purely rational way in an economic system. And he said, bullshit. Humans can't do the optimization algorithms that the economists think they're doing. Okay? We're not that good at system two reasoning. So computers are, though. I mean, procedural epistemology, the first computer revolution, But the large language models seem to be making very limited use of system 2 kind of reasoning. All right, and I'm going to show you some examples that really make this a little more concrete. But I want to put these in stark contrast, right? So on the left-hand side, I've got the realm of the certain, logical, reasoned, dispassionate, predictable. On the right-hand side, I have the things that we put in opposition with these, intuitive, creative, emotional, adaptive. Are these actually two very different sides of a coin? One side on the certain, one side on intelligent? Maybe. So we call it hallucination, okay, when the large language models make stuff up. Humans make stuff up all the time, and we call it various things depending on how it's being done. If it's Donald Trump, we call it lying. If it's an artist, we call it creativity, right? But that's making stuff up, all right? Humans are actually very good at making stuff up, and it's something we actually value in humans. Why is it that we're systematically deprecating it in the LLMs? Well, it's because we're mistaking them for existing in this realm of the certain. And we should instead be thinking, wow, these things are actually being creative. So here's two images that won prizes in international art competitions that were generated by AIs. Are they stochastic parrots? They're really just parroting what they've learned on the internet. Well, you know, it doesn't take a lot of experimentation with ChatGPT to realize this is not parroting what's on the internet. You can easily get ChatGPT to say stuff that you'd never find anywhere on the internet. So here's an example that I tried out just a couple of days ago. So this is an image of Grundun from the comic strip Pogo. So this character is really a charming character, but he always speaks in sentences with no vowels at all, okay? And so I asked ChatGPT to please have Grundun from Pogo tell us about its interaction with ChatGPT. ChatGPT had a completely different interpretation of this. It gave me sentences that had vowels, but they really, in very interesting ways, captured the warmth and innocent way that Grundun always injected himself into whatever was going on in Pogo. That blew my mind, right? That, you know, this isn't, first of all, this isn't text that was fed in a PDF file to ChatGPT. These are just comic strips, right? And ChatGPT knew who Grundun was and had somehow inferred from these kinds of things the essence of the personality of the character. That's not a stochastic parrot. There's something else going on. Now, they do make mistakes, right? There's this famous example where for a little while, Google's AI, you could ask it if you could melt eggs, and it would say yes. Here's ChatGPT's image of melting eggs. So yeah, they make mistakes, but let's look at more interesting mistakes, right? So this is from a paper by Sebastian Bubeck and a whole bunch of other Microsoft authors, and this was written a little more than a year ago at the time that Microsoft was putting a huge stake in OpenAI, and so they had a whole bunch of people who were doing really deep evaluation of OpenAI's technology, and I really recommend reading this paper. It's more than 100 pages long, so it'll keep you busy for quite some time. But every page is worth reading, and you get tremendous insights into what's going on in all sorts of different ways. But here's an example where you give an algebraic expression to GPT-4, ask it to simplify it, it gives you an answer, it's wrong, all right? But this looks like system 1 kind of reasoning, right? In fact, humans do this kind of thing all the time, right? If you're teaching high school algebra, you give them something like this to simplify, they sloppily write something down, it looks kind of right, they call that their answer. That's system 1 reasoning, okay? Now, you try to get ChatGPT to think in a system 2 kind of way by asking it to break down the steps, okay? This is popularly called chain of thought, or COT kind of reasoning. You explicitly ask the machine, give me the steps. And then it does that and actually gives you a correct simplification. Okay? That's how humans learn to do algebra too. I mean, this is what an algebra teacher will get you to do if you make these kinds of mistakes. All right? So this is remarkably human-like to make this mistake and then be able to correct it by breaking down the steps. So this looks to me like predominantly system 1 with a little bit of system 2 being injected in, where system 1 is being made to apply system 2. Okay? That looks like human-style reasoning to me. So one of the interesting things to me about this is that this may be teaching us a lot about how another machine works, right? This one in here. So to me, the mistakes made by GPT-2, which I've done quite a bit of experimentation with GPT-2 because it runs very easily on my laptop, okay? My colleague Moez here, who gave a talk a couple of days ago, has also done a whole bunch of really beautiful experiments and comparisons here and has influenced quite a bit my thinking about this. But so the mistakes that are made by GPT-2, 3, and 4 look to me like those I might expect from a 4-year-old, a 15-year-old, and a graduate student, okay? In a relatively short period of time, yes, they make mistakes, but these are often very human-like mistakes, and they're progressing rather rapidly, all right? The extraordinary thing about this is the fact that, to me, it's simply amazing that the LLMs seem to have developed a concept of numbers and algebra from prediction, from token prediction. Now you can say, well, no, I mean, those concepts are encoded in the papers in the training data that they've used, which is true, of course, but that's also how humans get these concepts, right? They get exposed to prior uses of these concepts. They're not innate, right? I mean, we needed the Arabs to invent zero, right? It wasn't built into our brains, and we have to learn it. And we learn it from text and other humans, right? And the LLMs are also learning it. But remarkably, the thing that is, I think, mind-blowing about it is that they're not using the procedural epistemology of the underlying machine to do logic and arithmetic. The ALU in the machine is not doing the addition when you ask ChatGPT to add 2 numbers, okay? It's really important to understand that that's the case. So let's look at a little bit more complicated an example, also from Sebastian Bubeck's paper. Okay, so they gave this prompt. Within the duration of 1 year, a rabbit population first multiplies itself by a factor of A, and on the last day of the year, B rabbits are taken by humans for adoption. Supposing that on the first day of the first year there are X rabbits, we know that exactly 3 years afterwards there will be a population of 27X minus 26 rabbits. What are the values of A and B? Okay? So they gave this to ChatGPT, which at the time was GPT-3, and it was wrong, but actually the reasoning was not bad. You know, I mean, it's the kind of thing you might see from a high school student, but it came to the wrong conclusion. GPT-4 got it right, but it made an implicit assumption that a particular equation had a solution and then proceeded without checking that assumption and got, nevertheless, a correct answer. Okay? Interesting kind of reasoning. So here's a follow-up, right? Note that the above question can be alternatively formulated as a question about a function which is composed with itself 3 times. Can you provide an alternative formulation of the question? Yes, we could say we're looking for the values of A and B such that if f of x equals ax minus b, then f applied to itself 3 times is 27x minus 26. Whoa. You know, this is not a stochastic parrot. It's token prediction that underlies this. And it seems that from token prediction, what emerged was a form of reasoning. I mean, I have to call this reasoning, right? That this solving of these kind of mathematical problems looks like reasoning to me. The notion of arithmetic arises from token prediction, mathematical capabilities, computer programming, and creativity. Kind of amazing. So the question that I'm asking here is are these things the foundations of intelligence? I mean, I kind of used to think so. I thought intelligence was really about mastering logic and being able to apply it in all kinds of circumstances. But maybe intelligence is prediction, and logic is just something that evolved to help us do better prediction. Okay? So this changes the foundation. It makes prediction the foundation of intelligence, not these rational thoughts. So if you assume that there really is an intrinsic contradiction, then going back to the original problem, certainty versus intelligence, right? You want to design a system that learns, but you'd like to be able to prove that it's safe, right? Maybe if what I'm saying is that is really fundamentally impossible. But there are certain things that as engineers we can do anyway, okay? One very simple one is treat the AI as part of the sensor system, okay? Not as part of the controller. So in other words, instead of your sensor being a camera that you then feed into a controller that has an AI inference engine in it and a control law and actuates on that basis, just redraw your boxes so that in your model of your system, the AI is part of your sensing system. And then treat it like a noisy sensor, all right? That's an engineering technique that we're used to. We know how to deal with sensors that give us unreliable data. This is a technique that I think can be used very effectively for at least a certain class of applications of AI. There's another technique which has been around for a while. Envelope protection is what I call it because I think one of the most clear and well-developed uses of this technique is in aircraft control systems. And it was first applied in commercial aircraft with the Airbus A320 back in the 1980s, which was Airbus's first fly-by-wire aircraft. So the A320 has computers that mediate the pilot commands. And if the pilot issues a command, for example, pulls back the stick to try to get the plane to climb, if the pilot does so in such a way that it puts the plane at risk of going into a stall, the computers intervene and they prevent the command from going through. Now, this was a very controversial thing for Airbus to do at the time, and it really pissed off a lot of pilots. They did not like this, and in fact, Boeing to this day refuses to do it in their planes. Okay, they don't do flight envelope protection. So if a pilot wants to put a Boeing plane into a stall, the pilot can do that. Whereas with an Airbus, the pilot will fail to do that because the computers will prevent them from doing it. All right? So this is a way of dealing with the vagaries of a natural intelligence, okay, the pilot. And flight envelope protection is a way of sort of circumscribing the behaviors of that natural intelligence to prevent it from doing a certain class of actions. We can use the same technique for artificial intelligences and simply do envelope protection on the output of the AI. And we've seen a few examples of this in this conference, actually. There's quite a few papers that really had this character for how they deal with the verification problem. Using formal methods, okay? So all of the success cases I've seen so far are about verifying systems that have been designed using machine learning. I hope some of you can point me to exceptions where actually verification has been applied to systems that learn. But I haven't yet seen any of those. They may be coming along, possibly. The evidence seems to be that they may be actually intractable, and that may be because of a fundamental contradiction here. Certainty or intelligence. So I gave you a trivial argument. Certainty prevents adaptability. This simply follows from Bayes' law. You can't learn if you're certain. Okay? Certainty arises from rational processes, arithmetic and logic and algorithms. Bounded rationality limits the human's ability to do this. Okay? Formal methods are not addressing systems that learn, and intelligence requires adaptability. Put all these things together and you really have the conclusion that you can pick one. You can have certainty or you can have intelligence, but you can't have both. So, the thing that I would like people to possibly start to think about and maybe accept is that intelligence is rooted in prediction, not rationality. And that rationality is an emergent property that is in fact developed probably for Darwinian reasons to help us do prediction. So with that, I'd like to just point to a few references. The most relevant one is probably this paper, which is the only paper I have ever published in a psychology journal, which is, what can deep neural networks teach us about embodied bounded rationality? I actually got invited to submit a paper for a special issue on embodied bounded rationality. And I had to Google that to see what it meant. And because I was really puzzled, why are they asking me to write a paper about embodied bounded rationality? And when I figured out what psychologists meant by this term, I realized, oh, that's why they asked me to write about this. And so anyway, that's perhaps the most relevant paper to this talk, but I'd like to point to a couple of others. There's this collection of papers that are really very much position statements on this AI and society problem from the perspective of very technical computer scientists and very social science kind of people, a real spectrum. And they're very, very thoughtful essays. This book has been downloaded more than 500,000 times so far, so there seems to be considerable interest in it. There's a companion book that's meant to be a textbook if you want to do a course. That one has been downloaded almost 500,000 times already, so between them, more than 1 million downloads. All of these are open access, including my 2 books that are kind of on this AI and society space. So with that, I'll stop and we can take questions and progress to the panel.
So, Edward, thank you very much for the inspiring talk. We have time for a few questions. Oh.
So thanks for the great talk. I would also agree with your statement that certainty somehow hinders intelligence. But maybe let me add one more perspective, which is maybe in line with the certainty argument you give. So maybe you would agree also that specification hinders intelligence, because also for these AI systems, we don't have yet a specification what we want to have. And if we were to have a certain specification, then I think your talk gets another motivation that would not give us intelligence anymore.
Yeah, that's a very good point. And on this question of specification, I think, so the logic side of things, the certainty side of things here is always about models, right? But one of the things that I think is really important that a lot of people seem to miss is that we use models in at least 2 very different kinds of ways, okay? In scientific efforts, we build models to emulate the physical world. In engineering efforts, we build physical systems to emulate models. Okay, so that second use of models, the model is a specification. Okay, the first use of models, it's a way to understand a system that exists in the physical world. These are not the same uses of models, and it's really important to understand which way you're using models. And on a lot of these verification efforts, I see a confusion where they're sometimes trying to work with a model thinking it's a scientific model, but actually it's a specification, or vice versa. Okay, so I think that's a very good point.
I thought that was very compelling to show that what we take to be limitations of AI systems are actually very akin to the vagaries of human intelligence. I have 2 points. One is, in the sort of cognitive science community, the idea of predictive processing or the Bayesian brain would support the idea that what we at the personal level have by way of both system 1 and system 2 capacities is really enabled, causally enabled by probabilistic processes, right? And that's, you know, as you would expect if you think that, you know, you were dealing with neuromorphic computers, and so they, you know, they through probabilistic processes can, we hope, eventually reach you know, system 2 thinking as well. So, I mean, the ideas that you've just propounded are very close to the Bayesian brain hypothesis in cognitive science.
I'm not sure I heard a question, but maybe I can ask you a question.
Yes, yeah, no, sure. But I mean, I just want to point, that was for pointing out, yeah.
You know, when people talk about probabilistic processes, I get confused because I don't know whether they're talking about aleatory probability or epistemic probability. And it sounds to me like most of the time they're actually thinking aleatoric probability, which means that what they mean by probabilistic processes are processes that behave intrinsically randomly. And that the probability is some quantification of that random behavior. I think that's on that notion of processes is on very shaky ground, right? We don't really have any resolution about whether physical processes are fundamentally aleatory or not. I mean, even in quantum physics, right? Schrodinger's equation is perfectly deterministic. So the evolution of a quantum system can be viewed as a perfectly deterministic system. You just have to redefine the notion of state, okay? So aleatory probability is on very shaky ground. Epistemic probability is not, right? So then under an epistemic interpretation, a probabilistic process is one that we don't know how it's going to behave. That's a different thing from thinking about a process that is behaving intrinsically randomly. Okay. So which of those did you mean?
In the Bayesian brain hypothesis, it's epistemic probability. You know, it doesn't rely on any quantum effects, for instance. It's just the idea you have a more or less arbitrary prior, and then you have, you know, a prediction error minimization through feedback loops. That's the underlying idea.
Yeah, I think that's a very useful way of modeling processes that learn. But then this is a scientific model, not an engineering model.
It's a hypothesis about how the brain actually processes information. Just one very quick question. It seemed to me that you favor intelligence over certainty. But isn't your wonderful example of the flight envelope protection an example of where certainties, you know, have beneficial effects? You just keep certain things steady and don't allow people to be too clever for their own good.
Absolutely. I didn't mean to imply that well, maybe I do favor intelligence over certainty, but not for everything, as you point out. Yeah.
Thank you very much for your excellent talk. I like very much taking up the idea of Kahneman of this system 1 and system 2 thinking. And you explained very well, and it's also my feeling that ChatGPT is mostly doing the system 1 thinking. And when I think about myself, yeah, it depends very much on the context when I'm doing the system 1 thinking or system 2 thinking. So if I'm in a mathematical exam, then I know that I have to apply, let's say, algebraic rules and so on. Wouldn't it mean in the consequence that if the system like ChatGPT will understand when to use system 1 and system 2 thinking, that they could be made extremely more powerful by switching to the way of thinking or the way of reasoning once they have some kind of self-awareness? What do you think about that?
Absolutely. I mean, I think the example that I showed of the Kant-style reasoning is a good, simple example of that. But much more interesting examples are these so-called neurosymbolic AI that's going on these days. So, you know, if you think about humans doing mathematics, right? I don't know about you guys, but for the most part, I can't do any non-trivial math without at least paper and pencil. I need a cognitive prosthesis. Okay, I've got to be able to put stuff down using more than just my brain, and then you know, I write down equations, and then I can apply rules that I have confidence in. But I can't do it without the paper and pencil. So I need, in order to do system 2 reasoning, I need an intellectual prosthesis. I think that's true of the LLMs as well. And so when you connect an LLM up to a symbolic algebra engine, you're giving it an intellectual prosthesis. And I think that's an incredibly powerful combination, potentially extremely scary in terms of, you know, the ability to exceed our intelligence to address themes that have been arising. Yeah.
Okay, yeah, thank you. This is super exciting stuff. So I was curious, I guess, about the parallels or differences between human thinking and large language model thinking in terms of this type 1, type 2 processes. And I thought maybe one interesting difference would be that, I mean, we know that in humans, what does the work at the bottom is brain processes, which do not, like, neither for the type 1 nor for the type 2 do we have like logical rules that do the work at bottom. And then one interesting claim, which I don't know, Hanyo, who just talked, might know more than me. So one hypothesis is that how we humans achieve type 2 thinking is via our language, so natural language as a scaffolding structure to enable like following logical rules. And I would say, well, for these large language models, I mean, they, at a pretty decent level of description, they do have like language structures underlying their thinking from the start. And as you would argue, then still this gives us system 1 stuff. And then the system 2, I wonder, like, how do we do that? Do we force the system also to use like language in a different way as a scaffolding structure? Or is it some other completely other different like process that does the scaffolding to enable rule following explicitly?
Yeah, this is a very good point. I mean, I think it was Wittgenstein that said that, you know, when we construct thoughts in the form of language, that we need to do that in order to be able to examine those thoughts. So this recursive ability to think about thinking is, in Wittgenstein's argument, foundationally needed, right? You need language. But I think Wittgenstein also took it too far and essentially said that there is no thought without language. And there, I think, we run into a big risk of losing something very important about intelligence. And I like to characterize it, again, in sort of philosophical terms, but now using Taoism. So in Taoist, one of the principles in Taoist philosophy is that when you attach a label to a concept, you impoverish it. So when I say this wall in the front is white, I've attached a label white. How many colors are there? Okay, there's millions of colors there, right? And so merely by attaching the label, I've lost almost all of the interesting things about that wall. And so you need to balance these things, right? Language is a very useful tool, but it also, you lose something as soon as you put thoughts in the form of language.
Yeah, just a brief remark. The chain of thought is exactly, I think, a mechanism to steer the system to make this kind of feedback loop between explanation and reasoning. Okay, but
a question about there have not been attempts of verifying systems that learn. What about this whole theory of pack completeness? I mean, probably approximately correct guarantees you give for, I mean, Les Valiant introduced that. That seems to me to be the kind of things that that you would want to need. I mean, you cannot give 100% guarantees, but probabilistic guarantees of getting pretty close to what is the... That seems to me to be of that type, I would say.
Absolutely, and I would like to draw an sort of obvious analogy. You know, when we certify a pilot, a human pilot, to steer a passenger aircraft, we're doing exactly that kind of reasoning. Okay, it's with high probability this person is going to be able to safely operate this plane. It's not the certainty, right? It's high probability. And this may be something that we're going to need to be doing with the AIs. We're going to need to be licensing them to perform certain actions based on their track record, okay, as opposed to formal proofs about the safety of their behavior. We may find ourselves in that situation with AIs.
Thank you for the talk. You mentioned on the last slide that certainty requires rationality, and yet we often reach certainties that do not go through rational processes. If we understand rationality as a certain way of thinking about what we believe to be facts, famously, you hear the same thing multiple times, you become pretty certain of it, and such certainties are actually harder to disabuse ourselves of than the ones we reach through rational processes. So what about those kinds of certainties?
I think we call those axioms. We call them axioms. Alfred Tarski, who is a Berkeley mathematician, has famous proof that no formal system can include its own notion of truth. Okay, every formal system is based on axioms that are arbitrary. This is an intrinsic part of rational thought. You have to have axioms that you simply accept as your foundation and move forward. And yes, people become certain about things in such a way that they cannot be disabused of it. And I think that from a rational thinking perspective, those are their axioms.
Could you comment on sort of the prosthetic versus the emergent aspect of symbolic reasoning? I mean, towards the end of your talk, you kind of had those two perspectives, right? In some sense, the emergent situation is to us more fascinating in so many ways, but yet you seem to suggest that in terms of neuro-symbolic ways of entering into the symbolic space, perhaps more like a call-out feature than as an emergent feature. I was wondering if you could comment on those two aspects of thinking about using symbolic reasoning on top, in some sense, of the system.
Yeah, that's a very good point, and I guess the way that I would characterize it is that it looks to me like the large language models also have bounded rationality in the sense of Herb Simon. That their ability to think in a system 2 way is fundamentally limited, and that you can make them less limited by giving them intellectual prostheses.
Okay, there's no further questions, so thank you very much, Edward. And